We have made use of the work kinetic energy theorem previously, and the work kinetic energy theorem can be a very powerful tool for learning about a certain system of objects. The work kinetic energy theorem is stated as the total work done on an object is equal to the change in that object's kinetic energy. This could be phrased as an equation in this form where W net is the total work done by all the forces acting on an object. So what that means is I imagine I have an object and there may be some forces all pushing on that object in different directions. W1 would be the work done by force 1. W2 would be the work done by force 2. I could calculate W1 and W2 and so on with work equals FD cosine theta. And then when I calculate the work done by each of the forces individually, I add them all up to get W net. We also mentioned the existence of conservative and non-conservative forces. One way of phrasing a conservative force is that if work is done against a conservative force, it is possible to recover the work back again. Now remember, we visualize work as giving energy to an object. If I give energy to an object, increase the object's energy, I say that I'm doing positive work. Or when I calculate W, W will be a positive number. It is also possible to do negative work on an object. That's basically saying I would take away energy from that object. And in that case, if I calculate W, I would get a negative number. Another way of describing a conservative force is I could say that a force is conservative if the work that force does moving an object between 2 points is the same no matter what path is taken. Some common examples of conservative forces are gravity and the spring force. If there are conservative forces, there also will be non-conservative forces. A non-conservative force could be described as if work is done against a non-conservative force, it is very hard, effectively impossible to recover that work back again. Another way of describing a non-conservative force is the work done by a non-conservative force does depend on the path taken. Some common examples of non-conservative forces are friction and air resistance. So what do we actually mean by conservative and non-conservative forces? As an example, let's compare the work done by the spring force with the work done by friction. Now remember, when I say work done by the spring force, I mean the amount of energy the spring gives to an object as a result of the spring pushing or pulling on that object. So let's say there is a mass on a spring and the initial position of the mass is going to be here. And then the final position of the mass on the spring is going to be over there. Conservative forces say the work done does not depend on the path taken. So the amount of energy given to the mass does not depend on the path taken. Maybe the mass just took this path to go from its initial position to its final position. On the other hand, maybe the mass bounced back and forth a couple times. These are two separate paths. However, because the spring force is a conservative force, the work done on the mass, the amount of energy given to the mass by the spring force, will be the same for both paths. Now, let's contrast this idea with a non-conservative force. In a non-conservative force, the work done does depend on the path taken. So if I think of friction, the work done by friction, the energy given to or taken away from an object by a non-conservative force, will depend on the path taken. If an object is sliding across the ground, it will lose some amount of energy if it takes a very direct path. It will lose a lot of energy if it takes a very indirect path. Even though you have the same initial and final locations, the work done by friction, which will be a negative number because friction tends to take away energy, the work done by friction will depend on the path taken even though you have the same initial and final positions. For any conservative force, it is possible to talk about a potential energy that is associated with that force. On the other hand, There is no such thing as a potential energy associated with a non-conservative force. This is because the work done, the change in energy for a non-conservative force, does depend on the path taken. However, if you think about the potential energy due to gravity, you have an initial potential energy due to gravity and a final potential energy due to gravity. And whenever you look at the change in potential energy, you only look at the initial potential energy and the final potential energy. Delta PE only cares about the initial PE and the final PE. It doesn't ask about the potential energy at any moment between the initial and the final moment. Potential energy was described as an energy of position, and the difference in potential energy between two locations will always be the same. For the moment, let's step away from conservative and non-conservative forces and let's discuss conservation of energy. Let's consider several different types of energies. To be completely general, I'll call them E1, E2, E3, and so on. These energies could be anything: kinetic energy, potential energy of gravity, electric potential energy, thermal energy, anything at all. The following three statements are all equivalent. I could say the sum of all of the energies is equal to a number, and whatever that number is going to be constant. I could say the sum of all the energies at an initial moment is equal to the sum of all the energies at a final moment. Or I could say the change in energy 1 plus the change in energy 2 plus the change in energy 3 and so on will add up to 0. All three of these statements are just different ways of phrasing that energy is conserved. So we said for every conservative force, there is an associated potential energy with that force. Let's investigate a consequence of this. Well, the force of gravity will have a notion of a potential energy of gravity. The spring force will have a notion of a spring potential energy. But the force of friction implies, since it is a non-conservative force, there is no such thing as the potential energy of friction. Let's consider a scenario where only conservative forces are present and acting on an object. If I say that the total work done on that object is equal to the change in the object's kinetic energy, and we are assuming that only conservative forces are present acting on that object, then I could say the total work done by the conservative forces is equal to the change in that object's kinetic energy. Now, we said the total change in energy acting on an object must be 0. Since only conservative forces are present, then I could say the total change in energy will be the change in the object's kinetic energy plus the change in the object's potential energy, and that must add up to 0 because the total change in energy must be 0. Therefore, I could say that the change in the object's kinetic energy should be equal to the negative of the change in that object's potential energy. And therefore, I could say the total work done by all the conservative forces acting on that object is equal to the negative change in that object's potential energy. Let us now allow for the possibility that there are both conservative forces and non-conservative forces acting on an object. The work kinetic energy theorem tells us that the total work done, the work done by all the forces acting on an object, is equal to the change in that object's kinetic energy. If I want, I could think of the total work done as the work done by all the conservative forces plus the work done by all the non-conservative forces. So I could rewrite the work kinetic energy theorem in this form if I wish. Also, if I want, I could write the right-hand side of the work kinetic energy theorem as delta KE plus delta PE minus delta PE. Essentially, I am only adding 0 to the right-hand side of the work kinetic energy theorem, but I'm being creative with how I choose to write 0. Now, what is the motivation for actually writing the work kinetic energy theorem in this form? In the previous slide, we found that the total work done by all the conservative forces acting on an object is equal to the negative change in an object's potential energy. So if I look at the work kinetic energy theorem written in this form, I recognize that this term is going to be the work done by all the conservative forces acting on an object. If this term is the work done by all the conservative forces acting on an object, then whatever's left over, this term must be the work done by all the non-conservative forces that are acting on an object. When you are solving problems in this chapter, a useful strategy could be to remember that energy is never truly lost, but sometimes it might look like energy is lost. When this happens, it probably isn't that energy is actually lost. Energy can be converted into a form that cannot be recovered or easily retrieved. Some of these examples might be energy being converted into thermal energy, sound energy, light energy, and so on. So, to address these problems, it could be helpful to determine the initial energy of a system. You do your calculation and you get some number for E total for the initial moment of a system. And then you do a calculation, you find the final mechanical energy, which is basically find the final energy in terms of kinetic energy and any potential energies that might be around in your system. And if there is an imbalance between these two values, the initial energy and the final energy, consider the possibility that some of that energy may have been lost to light, heat, sound, and so on.